Okay, coming back here. So, okay, so one of the problems that you have in hypothesis testing is called multiple testing. Now, what is the concept of multiple testing? Imagine you have some random variable like x1 here. X1 could be that, okay, so let's say x1 is your body weight, or your x1 is basically body weight that you've lost. Let's just say, okay, I'm just taking a real example that I've seen. X2 is, let's say, how much coffee you drink. Okay, x3 could be how much tea you drink. X4 could be how much chocolate milk that you drink. Xn can be how much coconut oil you drink. In some parts of the world, people love coconut oil, right? So let's assume there is a crazy guy who says, hey, I will test whether you will lose body weight or not by comparing against tons of other things, right? Tons of other things. So here, imagine if I have a significance level of something like 5% and n is very large. This is important. I'm comparing body weight lost with lot of other things that people typically do. It could be all sorts of useless things, right? Whether somebody is eating more rice, more wheat, whatever it is. Now, because of the way the whole hypothesis testing itself is designed, that's the important part. Because of the way it's designed, we always compute a p-value. Because any statistical test will have type 1 and type 2 errors. It could so happen that you can say, hey, reducing your body weight, okay, lowering body weight is not related to drinking tea. Let's assume this is drinking tea. It's not related. Okay, lowering body weight is not related to drinking more coffee. Okay, you're doing these experiments, right? Most of them will become false. But because you have type 1 and type 2 errors, the way you've designed your null hypothesis and alternative hypothesis, because of the way you've designed it, it could so happen that your x1 could turn out to be correlated with x4. Your x4 could be like eating chocolate. I think I've read some article which says that, hey, you can lower body weight by eating more chocolate. Come on, for God's sake. Most chocolate has so much sugar, unless it's extremely dark chocolate, right? So what some of these so-called researchers do is they misuse the p-values and hypothesis testing by saying, I'll compare this thing with many of them. They forget the fact, because they probably don't understand how hypothesis testing itself works, right? Because of that, what they do is they look at errors, right? They are this again. Remember, any hypothesis test in the world will have errors. The way based, it could be either type 1 or type 2, depending on how you designed your H0 and HA. The problem in this is here, because X1 is being tested with all of them, and in all these cases they're using the same significance level, right? They might come to incorrect conclusions like this. And I've also seen other extreme behavior in p hacking. Multiple testing is one way of doing p hacking, right? They'll come and they'll write a research paper saying, hey, you can lower body weight by eating more chocolate. And they say I have a p-value of 0.02, which is less than 5%. So this is statistically valid. But there are two problems here. They don't tell us of all the other tests that they have done. That's one problem. That's one way people do multiple testing. And when you do multiple testing, some errors will occur, and that's not being reported. If they told us that, yes, I have done 100 other experiments of which chocolate turned out, others failed, any reasonable statistician or even scientist can say, hey, what you're going through is some form of type 1 or type 2 error, right? That's one. Other major problem is they just do these experiments on only 30 people or 40 people, right? That's too small a statistical sample, just too small. I've seen more extreme variety also. So let's assume in their control and treatment, okay, let's assume they have control and treatment. Suppose they have some 100 people in control, 100 people in treatment. Then in p hacking, what they do is, suppose this is a sample of 100 people, this is a sample of 100 people. What should you do? You should compare whatever results you got in control and treatment and be judicious about it. But in p hacking, also called as p harking, they take a small subset. They take a small subset of these people. They also take a small subset of these people, right? They may not pick these subsets always randomly, right? And they compare these two. They're not using the whole data. They're using a subset of data to tell a story saying that yes, XC and XT are related or not related. So the reason why a lot of modern scientists, especially in the healthcare domain, they don't like hypothesis testing is because there is so much of misuse of hypothesis testing, either because of multiple testing, or either because they're not taking truly statistical samples, or they're taking too small a samples, or probably their data, because they're doing multiple testing, has some form of type 1 or type 2 error. And in all of them, everybody uses 5% significance level. And this is incorrect. So one simple solution, very simple, often used, is called as a Holm-Bonferry correction. The idea behind it, again, I'll not be able to go too deep into it, but the idea behind Holm-Bonferry correction is this. It says, when you're doing so many tests, don't use the same significance level for all the tests. Have much more stringent alpha values. So your p-values that you got, right? You would get, like for each of them, you'll get some p-value, right? For this, you might get a p-value of 16%. For this, some 10%. For this, you might get a p-value of 1%, and so on and so forth. For this, you might have got a p-value of 20%. So the Holm-Bonferry correction basically says, don't use the same significance level for all of them. Make it stricter as you have more tests that you're conducting. That's the core idea behind it. The core idea that they try to employ is, don't fix this. Keep this changing, especially as the number of multiple experiments or multiple tests that you're conducting, as it increases, make the p-values that you have much more. 1% will not cut them. Make it much more stringent, right? Again, simple solutions, they work reasonably well in practice. This is one that a lot of bioinformatics folks use. Okay, cool. Another much more simpler solution, okay, mostly like a data science solution, is called as out-of-sample randomized tests. This is inspired from modern data science. Suppose this is my whole sample of data, all observations. This is my total observations that I have. They say, break this data randomly into two groups, A and B. Whatever hypothesis you want to build or initial hypothesis testing you want to do it on this data set A. This data set A will have control and treatment and all that. Okay, control in A, treatment in A. Okay, build all of your hypotheses, all of your initial experiments, do it in this. Then comes the fun part. Then they say, whatever conclusion you got, whatever hypothesis you have tested here, they should also hold on B. You have not seen B till now, remember. You took the total data, you broke it up into two parts. Whatever hypothesis or conclusion that you came here, the same conclusion with similar statistical behavior should be observed on the test data also. This is inspired from train test splits. This is called train. This is called test split in machine learning. Again, this is inspired from that machine learning system where you say that I have some training data on which I will build my models. In this case, my model is the hypothesis. And whatever conclusions I get, I will test it on this held out data. We typically call it as a test data. Now, this is called in statistics as out of sample randomized tests. Why is it randomized? Because the total data, we are breaking it up into two random samples. And whatever hypothesis we have built using this subset A, we are going to test that hypothesis again on the out of sample B, which we have not touched till now. That's the idea here. Okay, again, very simple, works reasonably well in most situations.